Yeah, so I'm Nico. I'm a postdoc at Aalto University, where I'm working with Noah, for example, and Aki Bechtari also on like the general Bayesian workflow. Yeah, I think that's enough introduction, right?
Yeah.
Okay. Okay, so this seems to work. So you can find the slides down there on the URL. I'm not sure what this is legible actually. Right, so I'm going to talk about practical, model-specific automatic reparametrizations for Bayesian inference. And there's kind of a conflict there in the title, right? So it's supposed to be practical, but it's also supposed to be, so which is sounds more applied. Then it's also for Bayesian inference, which is very general, right? And then it's model-specific, which is again very like specific to a model, but then it's supposed to be automatic, which is then again also very general, right? So, but I think it makes sense actually this time. So I'm hoping you will agree. And actually, 1 second, I want to start a time. Sorry. Okay, so this is what I'm going to talk about now. So first I will tell you where all of this belongs into this bigger Bayesian workflow picture. Then I will tell you what basically came before, what I'm doing. Then I'll tell you what I'm doing, how I do it, and where, for which kind of models we can do it. And then finally, I'll tell you what comes next. All right. So if you've ever done any Bayesian data analysis, then you know that it's usually smooth sailing, right? So you find some data on the internet or lying around on the street. You squint at it, build a model, fit the model, make a decision, and celebrate because it was so easy and everything just went perfectly, right? That's how it's always goes. Of course, so it's not like this. If only we were like that, we would be out of our jobs probably. But yeah, so I aim to make this fitting the model easier for practitioners. I think it's the same goal that Amal has, I think, or that many of us have, because you don't want the people who are experts in all the other things to also be experts in like the theory of sampling from posteriors. Right? So why would they want to know about this? And I think back then, 20 years ago, if you were doing Bayesian inference, then you would even have to code your own sampler and everything. And things already have gotten much easier now, but things could be even easier, right? So this is what we want to do. Okay, so the problem is, or rather the problem that I'm tackling now is that depending on your data, the same model can behave very differently if you're trying to sample from, right? So the prototypical example is a hierarchical model where depending on how strong your likelihood is, you either get this nicely behaved shapeless blob on the top left, or you get a funnel, which then makes it very difficult to sample from if you're using HMC, for example. Right, so the left one would be the classical non-centered parameterization with a weak likelihood, and the right one would be a centered parameterization with a weak likelihood, where you can't easily descend into this funnel. And then what HMC, for example, would tell you is that you had some divergences, and then these divergences are in some sense spooky because you know that there's something lurking down there in the cellar, but you're not quite sure what it is and whether it will impact the decisions that you want to make. Okay, so now to add insult to injury, right? So if you now have tuned your model to give you this top left shape, now suddenly you have the same model but different data, so maybe just more data. Suddenly you have a strong likelihood, and now what used to work perfectly now gives you the other funnel. You again encounter divergences, but then if you were now to switch back to the so-called centered parameterization, then again sampling works out fine. And so we are hoping to make this easier for practitioners, not have to do this manually, because sometimes doing this manually works, right? So maybe you start with the centered parameterization, you go to the Stan forums or whatever, and then they tell you, oh yeah, just non-centered, then everything works, right? And sometimes it works, sometimes it doesn't work. Sometimes it's infeasible because maybe you have many tuning parameters, which are not easy to tune by hand, and sometimes you might even have to do something completely different. All right, so this is what we are trying to solve. Right, so there already has been similar work. But so first of all, I'm talking about now, well, general reparametrizations, and now this non-centering is in some sense some specific case where you do nonlinear reparametrizations automatically. But of course, whenever you fire up Stan or PyMC, or I'm guessing QQPy as well, then automatically what you are doing are some automatic linear reparametrizations, right? So you're trying to learn the scale of your parameters or the correlations of your parameters to try to make HMC sample as efficiently as possible. And then there also have been approaches to do this parametrically for nonlinear reparameterization, similar to what we are showing now. And there also have been approaches to do this completely non-parametrically. So very generally using neural networks or whatever for nonlinear reparametrizations. But then these approaches are either rely on extra assumptions or don't work as well, or just in general are a bit fragile. Right? So we are trying now to combine these two approaches by using what is being done routinely for linear reparametrizations, combine this with the other approaches to do nonlinear reparametrizations generally and relatively cheap. Okay, so how would you, or how and or why would you want to learn linear reparameterization? So the goal is to make your posterior look similarly to this shapeless block that you had before. So you don't want any correlations, you don't want any funny funnels, you just want your shapeless block, because then and either your variation inference or your HMC sampler can sample very efficiently from this. So, and then how this then currently, or how this can be done, or how this works in practice, is that you're trying to learn the covariance of your posterior, and trying to successively improve this estimate. And then how this, I think, currently gets done in the main frameworks is you can either use a diagonal covariance estimate or a full covariance estimate. You can also do other things. And of course, all of these things have different properties, right? So are more or less costly, perform more or less well, and so on. All right, so this is essentially what Stan would do now. So you are starting with something which is very badly correlated. So this is now some high-dimensional Gaussian posterior, where I'm showing you the projection of the two parameters which are most highly correlated after our linear parameterization that we have done so far. And so you can see that it starts off very highly correlated. So these red black dots are reference samples from the posterior in the current frame of projection. The blue dots are the current samples, and then the red dots, which will appear in a bit, are the samples from the previous warm-up window. And so this is what you always do whenever you stand, for example. And so in the first step, usually in learning this linear reparameterization, is first to find where all the probability mass is. Right? So this usually happens very quickly. And then most of the time, so basically the remainder of this of these rectangles on the top is spent trying to learn this correlation structure or the scale structure of the posterior. So then how this proceeds now, once it has found this typical set, it explores the typical set, learns something about the structure, and then it spends some time doing that. And then having done this, it transforms the posterior. Right? And then you see now the correlation already has decreased a bit. And basically, you just repeat doing this on and on and on a bunch of times until eventually your correlation gets lower and lower. And at some point, you end up at this shapeless block that you want to be, because then you can just sample efficiently from it. And how this works is then usually you have like 25, 50, 100, 200, and then 500 samples just trying to learn this structure. All right, so what do? So we're trying to do this automatically for the user in some sense. So after having set this up, this should work without user intervention. It's supposed to be windowed because we're trying to reuse the samples that we obtained during the regular warm-up, during which we also try to learn the linear reparametrizations. So this is supposed to be nonlinear because it already works for the linear case. And we are not only doing parametric reparameterization, but so we don't want to fit some fancy neural network. We just say, okay, we know based on the model structure, we know which kinds of parameterizations would be appropriate for this model. And we're only trying to do a little work, but this may take us very far. Great. So the first step is to set up some model-specific continuous family of parameterizations. And how this works, for example, is now for a hierarchical model would be something which interpolates between this non-centered and the centered parameterization. Right? So in the middle, you see some posterior that I set up such that there is some ideal centeredness where we have the shapeless block, but neither the non-centered nor the centered parameterization give you good sampling efficiencies because you have funnels either way, whatever you do. And then you can, and then you can essentially interpolate between this linearly, and these are always the same samples, just so from the same posterior and the same samples, just parameters differently, right? So you see, you can interpolate this between these two things, and there is something which gives you this block that you want. Great. So how do we do this? So reuse the warm-up samples that we already gotten, and then at each of these iterations, at the end of each of these windows, we use these samples to try to minimize, to try to find some reparametrization parameters which minimize the Kullback-Leibler divergence between the obtained samples that we got, the posterior that we, the reparametrized posterior, based on the warm samples that we got, towards some normal approximation of the reparametrized warm-up samples using the sample mean and the sample covariance. And then this is, so now this is a very cheap approach because you already got the samples, and to evaluate this, you only need to evaluate the prior essentially. So this is very cheap, and you only have to do this once per sample, for which you potentially spend many hundreds gradient evaluations to get the sample, right? So I've got more details and animations on this link from a previous slide where I talked about this, because I wanted to show you some examples where this would be helpful. I'm going to skip more of the details, and I'm just going to go to the examples. And yeah, all right, so let's go there. So I've prepared 2 examples, and I'm actually faster than I thought it would be. So I think we have more than enough time to talk about both of them. So the one example is about Hilbert space Gaussian processes, which is, I think, well, not a good name for this method, but what this essentially is some way to discretize Gaussian processes, right? So we might know, might not know that Gaussian processes scale. If you do this exactly, scale a bit badly with the number of observations. So usually this scales cubically with the number of observations, which is pretty bad if you want to do this like a few thousand times, or if you have many observations. And then the other example is a random walk model for infectious diseases. Where essentially then the point is that even though these compartmental epidemiological models, well, work fine and have some theoretical justifications, it's also clear that they don't capture the behavior of infectious diseases in human populations, right? So maybe they capture the behavior of infectious diseases in animal populations because they don't really react to what's happening to the others. But as we have seen in the last years, this is not helpful for human behavior. Right, so so now I want to tell you first that both of these examples are basically put some form of hierarchical prior on the parameters, which would then be in danger of exhibiting these funnels, but then would also be amenable to our method, getting rid of the funnel and easing sampling from these posteriors. All right, so then let's recall a hierarchical model, essentially one where they have a prior on some hierarchical parameter, where at least the scale parameter somehow is a function of the other parameters. That's because this then gives you the this funnel behavior. Okay, so yeah, I think this is big enough. Great. Hilbert space Gaussian process is essentially a Gaussian process which tries to trade linear scaling, so something which is good, for the danger of encountering funnels, which is something that is bad, right? And how it does this? It decomposes this Gaussian process realization on the top row into a weighted sum of basis functions, right? So these are the basis functions. These are currently just 5. And then here you have different basis function weights. And these are now actually, I think, 40 or so, right? But then if I show you 40 basis functions, then you don't see anything here. So it's pictured this way. And then if you are like me and you don't know anything about Gaussian processes, then you can just think of this as some way to regularize your latent function, right? You're not trying to catch every oscillation of your data because this would be unreasonable, but you're also not sure how the latent function should look in the first place, right? You want to have something which can capture many things, but which doesn't overfit. But now, after you have done this discretization using these HSGPs, then you have your Gaussian process represented as the sum of basis functions. But now, because these the prior on the basis function weights, they now depend on the hyperparameters of the Gaussian process. This will then give you, again, this hierarchical structure, because then these basis function weights have a prior which is essentially normal with some standard deviation, which depends on your Gaussian process hyperparameters. And then you can visualize in 2 ways. So this would now basically be the prior distribution of the centered basis function weights. And there you can see then with the increasing frequency of the basis function, your weights decay. But then they have some prior structure which depends on the hyperparameter. Now you can switch this to the uncentered, non-centered parameterization, and then they all have the same prior, which would then be a standard normal distribution. But then this would now lead to the basis function being scaled. Now, depending on the Gaussian process hyperparameter, which would be now this log length scale, different basis functions would then get different weights. So, for example, if you have a large length scale, then these higher frequency functions get downweighted, and if you have a smaller length scale for the Gaussian process, then the weights for these basis functions are essentially the same. And then, of course, then also the realization that you can sample from this prior chains, right? So this is now a wiggly one, and if it's less wiggly, then it looks maybe like this or so, right? But then, so you gain this linear scaling, but you get this danger of funnels because you have a bunch of hierarchical parameters here. So this can be, these are not 40, but could also be that you need 80 or something. Then maybe you have more than one Gaussian process, so this can be difficult to tune by hand. Or I guess impossible, because you don't want to do this, right? All right, so this is how they work and how they trade the linear scaling for the funnels. And now this would be now some example of some data that I found online. So this is now a simulated motorcycle accident. And so what I'm guessing what you see here, I actually don't know the data set very well, but I think this is an acceleration time series, right? So then at the beginning, the acceleration is 0. Then as it crashes, it gets decelerated and again accelerated. And you can see from the data that apparently there's something going on with this measurement device that makes it capture the acceleration well. Not a lot is happening, but then as soon as a lot of things happen, there's much larger measurement error, right? Then this can be, for example, modeled, having basically no expert knowledge. You just know that, okay, so things should be similar to observations that happened in a near time frame. And you can basically say, okay, my model is some Gaussian process on the prior, so on the mean, so the mean should be more or less smooth. And then this varying standard deviation should also be more or less smooth, right? So this is a flexible model to capture basically whatever you want without a lot of domain knowledge, but the only domain knowledge being that things shouldn't vary too quickly. And then the problem here is now it's usually such that these higher frequency basis functions, so the ones that don't have as many oscillations, they are usually much more closely determined by the likelihood, because you know more about the slow wave number basis function, but you know much less about these high frequency basis functions, just because your data would have to be much more accurately resolved to capture the behavior of these high frequency basis functions. And you can see this, for example, here in this lower plot, where these black lines are the posterior marginal standard deviations, and these bands are the prior distributions of the parameters. You can see that so the higher frequency basis function weights are now essentially equal to the prior because you don't have any information on this, but then the basis function weights for the slower basis functions, they are more determined than the other ones. And actually, this is not an extreme example, so you can see here that there are a few things which are relatively closely determined, but not super closely. But this kind of illustrates the point that for these high frequency things, you don't know as much as for the other ones. All right, and then, okay, so now, let me check. Okay, so maybe actually we skip this because we're now at 18 minutes. Okay, so then I had some other random walk example prepared. We'll skip this, and then the point was that so for different age groups, the number of deaths that you observe is differently high because elderly people are much more susceptible to COVID. And then if you have some random walk model, then depending on the age group, your likelihood would be differently informative. Then you would need to use different parametrizations for different age groups, and then also for different times, because during a peak, you know a lot about your infectious process, but during the valleys, you know very little. Great, and that brings me to my conclusion. So what comes next would be you, because I would be hoping to find some good posteriors or some good models which would help me try this out and demonstrate the practicality and the usefulness of this method. And these include, for example, so these prototypical hierarchical models. These include these discretized Gaussian process, models, random models as well, but also anything which fails generally to sample easily, but could maybe benefit from an approach such as this. All right, that's all, and thank you very much.